I am just reminding you that the last thing we talked about is the fact that the four quadrants of the Cartesian plane can each be given numbers, starting off with the one where they're all positive. And you remember this from trigonometry, hopefully. And yet sometimes talk about the cast rule. We're not talking the cast rule today, which is something we will be talking about eventually. But right now we're just talking about numbering the quadrants from 1 to 4, starting with the one where you have positive x and positive y, going counterclockwise until you get to quadrant 4, which is down here. All right, so that is what we're talking about. Let's get to these graphs. I'm going to start off, let me grab my stylus here. I'm going to start off by looking at a situation where the function is an odd degree function, right? So let me remind you now, odd degree functions are like linear functions. Okay, I think we can all agree that a linear function is an odd degree, meaning it's a degree 1. A degree 1, an odd number 1, makes it an odd degree function. What's another example of an odd degree function apart from a linear function? Give me another odd degree. Anybody, give me another odd degree function that you can think of. A cubic function. Thank you, Noah. And in fact, that's the one that we're going to be seeing in this graph in a minute. So let's think of a linear function, though, to start us off. This red line that you're seeing right there is obviously linear. And that's an odd degree. Now, if it was a linear function, right, like that red line, and it had a positive m, so the slope was positive. We all knew from grade 9, we're in grade 12 now, right? We all knew from grade 9 that a positive slope means that you're going up as you go from left to right. So it's a rising function. A positive slope means that you're rising as you go from left to right. Well, that's what you would have for this red line. It's a positive slope. It's a linear function because the m in this case is positive. So odd degree and a positive lead coefficient actually has an end behavior which goes from what we call Q3 to Q1. Now, what am I saying when I say that? Am I saying that the function only goes through Q3 and only goes through Q1? No, I'm not saying that. I'm saying that as you move further and further to the end of the function, towards infinity, the function, this red line, continues into Q1 and starts off somewhere in Q3. It can, in fact, a linear function, which is a positive slope, it can pass through Q2, it can pass through Q4, but it's going to, at some point, leave those two quadrants and end up, which is why they call it end behavior, in Q1, and it's going to start somewhere in Q3. That's all we're saying. And that's what end behavior is. What happens as the function goes from minus infinity to plus infinity? Where is it starting off at minus infinity? Where did it go from? And I'm saying it's going to go from Q3. Every single odd degree function with a lead coefficient which is positive is going to behave like this red line here. So that means that if it was even a cubic function, like Noah said when I asked the question, Noah talks about a cubic function being an odd degree function. If that cubic function had a lead coefficient that was positive, it would behave the same way. In other words, look at this red line, the blue line. The blue line does start off in Q3, and if you follow it along, you can see my mouse sort of moving along here. And even though it passes through Q2, it doesn't stop there forever. At some point, it ends up over here in Q1 and then stays in Q1 all the way to infinity. So the linear function and the cubic function have something in common if they both have a lead coefficient which is positive. So what is an example of a lead coefficient being positive for a cubic function? Well, I'll write you one. So what if I had y equals, let's say, 6x cubed minus 4x squared minus 9. I just made that up. Okay, so if that's the case, then the positive lead coefficient of 6 along with the x cubed, which makes it an odd degree function. Remember, the degree of the function is dictated by what the highest exponent is. Even though there's an x squared term, the x cubed is what makes it a cubic function, a degree 3 function. So it's an odd degree function, has a positive lead coefficient. It's going to look something like this blue line right here. It's going to start off in Q3, end up in Q1. It may pass through other quadrants, but in terms of its ends, that's what it's going to do. Okay, so that takes care of the first graph. And the first graph, remember, is a leading coefficient being positive and an odd degree. Those are the two conditions that come together for end behavior, such as what you're seeing there. So I can just touch that thing right there. Another way of saying this is to say Q3 to Q1. So that was what was behind that blue box. Let's move over now to the next graph, excuse me, which shows you the opposite situation, which is a negative lead coefficient. It's still an odd degree, but it's a negative lead coefficient. So look at that red linear function. It's still an odd degree function. A straight line is an odd degree function. So that function is a negative slope, and you know that a negative slope, a negative m, means it's going to be dropping as it goes from left to right. It's going down. What does that mean in terms of its end behavior? It's going now from Q2, which is where this, whoops, sorry. Let me go back there. It's going now from Q2, but ending up in Q4, which is what this box is saying, Q2 to Q4. Now, that's for a linear function with a negative lead coefficient, but it turns out that that is exactly how all other odd degree functions with a negative lead coefficient behave. So you'll see this blue line behind it, and I'm tracing it out with my stylus right now. That's a cubic function that has a negative lead coefficient, and it's doing the same thing in terms of end behavior as the linear function. It's going to start off somewhere in this quadrant in Q2, and it's going to end up somewhere in quadrant 4. Yes, it does pass through quadrant 3. That's clear. You can see it passing through quadrant 3, and that's fine, but doesn't stay in quadrant 3. Right? As you go further and further to the end of the function, so either to the left or to the right, the function is going to go more and more towards Q4, more and more towards Q3 as you go negative infinity and positive infinity. So that's what we're saying so far. Yes, Jana, go ahead. No, no, no. The blue. So, yeah, so the question was: is the red line? Sorry, say the question again, please. Is the red line what? No, no, no. They're two different functions. What they have in common is they're both odd degree functions with negative lead coefficients. That's what they are. That's what they have in common. So when it has an, what we're saying is that when you combine those two things together, odd with negative lead coefficient, that the function will always have the same end behavior, right? So they're both behaving the same way in terms of end behavior. They're both going from quadrant 2 to quadrant 4. That's their overall trend, is what I'm saying, Janai. Does that make sense? Or do I need to say that again? Okay, great. And thanks for the question, by the way. So the other thing is that there's another way of expressing end behavior that we need to also be able to do. So the quick way is to say Q3 to Q1. But especially for some of the other parts of this course, you need to have another way of expressing end behavior. And I want to go over that with you now. Let's go back to the first graph. The first graph we said was Q3 to Q1. So as you go towards negative infinity, the graph is going further and further into Q3. And as you go towards positive infinity, the graph is going more and more into Q1. Here's the other way that we have to be able to express it. As x tends towards minus infinity, so as you go this way along the x-axis, you can see my cursor moving along the x-axis this way. What's my y value doing? Well, my y value is going down further and further. So movement this way leads to movement down, right? Oh, sorry. So another way of saying this is to say the following, that as x tends towards minus infinity, y tends towards minus infinity as well. That's also another way of expressing end behavior. So as y goes negative, sorry, as x goes negative, y also goes negative. Yes, no, please go ahead. Yes, and Noah is asking whether when you're talking in behavior, you're always going from left to right. You're absolutely always going from left to right. Yes, right. So and some people when they and I'm glad that you asked that question, Noah, because some people would call this Q1 to Q3 because they're going from the right to the left, and I would always sort of take a half mark off of that because you always go from left to right. It's the same way we read. I know that in some cultures, in some languages, you read the other way, but think of it as the way we do it in English, is you read from left to right. All right. So we're going to go from Q3 to Q1, not Q1 to Q3. But on the other hand, you also have to ask, as I move towards the left, which is going towards minus infinity, it's another way of expressing end behavior, where is the function going? So as I go this way, the function is going down this way. So that's why I can write it as you see me written as I've written it here. As x tends towards minus infinity, as I move this way along the x-axis, my function is going down along the y-axis. That's why it's going down into Q3 here. So that's one way of expressing it. You cannot express end behavior, though, with only one side. You also have to express end behavior the other way. What happens as I go to the other end? What happens as I go towards positive infinity? So as I move, so you can follow my cursor, as I move this way, positive infinity, going this way, where is the function going? Well, the function seems to be going up. So the other way that we can say this, other side of the end behavior, is that as x tends towards infinity, y tends towards infinity as well. So for you to express end behavior without using the Q this and Q that, you have to be able to talk about what's the function doing as I move towards negative infinity and positive infinity. And that's what this way of describing end behavior means. So this is saying the same thing as Q3 to Q1, but later on in this course, you have to be able to describe end behavior not in terms of Q3 and Q1, so I'm introducing it from now, right? What's happening as I move towards either end of the function, right? As I move towards the left and as I move towards the right, where's the function going? What y, when I say the function, what's the y value doing? Is the y value increasing exponentially or not necessarily indefinitely? I should say not exponentially, right? Then you say it's going towards infinity or negative infinity. So in this case, as x move towards negative infinity, y is moving towards negative infinity as well. As I move left, I'm moving down. As I move right, I'm moving up. And that's what that box is saying. So let's now get to the second box, right? This box over here, and ask the same question. We call this Q2 to Q4. So we said that the function as you move from left to right, and again, Noah asked a very good question. As you go from left to right, then you're going from 2 to 4, not from 4 to 2. Could I be reading from right to left? As you go from left to right, you're going from Q2 to Q4. So that's why we said it this way. You see that this is what we have right here. But how do we express it with the other terminology? How about this way here? So as x tends towards minus infinity, as you go this way, how should we express our y? Where is y going? As x tends towards, yes, no, please go ahead. Mm-hmm. Well done. Well done. There you go. Absolutely correct. Excuse me. So is everybody clear on what Noah just said and why his answers are right? If you're not, you need to stop me, right? I don't mind going over it again. So as I move to the left, as I go further and further to the left, the function is going upward. As I move to the right, function is going downward. So to go towards positive infinity, towards that end, function is going downward. As I move to the left, it's going upward. Even degree functions now. Even degree functions. So for even degree functions, so we're talking about like a quadratic function, which we've talked about before. A quadratic function obviously is an even degree function. That's an x squared function. So the highest power there is 2. So that's an even degree function. And you did a lot of work with quadratics back in the day. All right. So if you look at that red line represents a quadratic function with a positive a. You know the y equals ax squared plus bx plus c. Okay. All right, okay, folks. I see you're all exchanging contact information here. I just hope that you're not going to be collaborating like when you're doing a test or anything like that. That would not be right. I just want to be clear on that. All right. I hope that. Okay, everybody clear on that, so that this is not for when you want to do a test or anything like that. Okay. All right. Perfect. Okay. Let's get back to what we're doing here now. So even degree function, like for instance, x squared function, that's an even degree. That function, if it has a positive lead coefficient, like a positive a, we know we normally say it opens up, all right? So if it opens up, it looks like that red line. That red line is a quadratic function that opens up because it has a positive a. Well, it turns out that that function would also be a representation of any even degree function with a positive lead coefficient, such as a quartic function. A quartic function also has a degree which is even, and if that also has a positive lead coefficient, it's going to behave just like a quadratic function. So what about the end behavior of a quadratic function? Can anybody suggest? Okay, Noah is saying Q2 to Q1. What do other people think? Right? Are you going to agree with Noah on that one? He thinks it's Q2. I'm not going to say he's right or he's wrong. I'm just asking what other people think. Is Q2 to Q1 correct for that? What do other people think? Agree with Noah, Rachel says, and Joel also. And okay, all right. So you're right. Okay, you're absolutely right. So there you go, Q2 to Q1. So again, we also have to, and by the way, the blue line is a quartic function, which has the same characteristics of the quadratic function. It goes from Q2 to Q1 because it's quartic, so that's an even degree, and because it has a positive lead coefficient. So there you go. Now, I want you also to try to see if we can describe this in terms of end behavior using as x tends towards minus infinity, etc., etc. So let's see if anybody can help me out with this. As x tends towards minus infinity, what's my y doing for this function? So you notice a q2 to q1. We got that. We're clear on that. q2 to q1 makes sense. But my question now is, as I move to the left, right, what's my y doing? As my function moves, as my x value, no, that's not that function. As my x value tends towards minus infinity, what is my y value doing? Can anybody answer that question? Where is my y going? I want to express my end behavior the other way, right? That second way that we did for the first one. As x tends towards minus infinity, where is my y going? Nobody can hazard a guess on that one? Only Noah? Okay, Noah, go ahead. Okay, good for you. There we go. There we go. That's exactly right. Is there anybody who's not clear on that? Right? Is there anybody who is not clear on that? For the red one, Jenna is asking. Well, it works out that it's for both functions. So remember that they both, well, the blue graph has the same characteristics, Jeremiah, as the red graph, right? In terms of its end behavior, it has the same characteristics, is what I'm saying. So what I'm saying, Jeremiah, and for everybody else who is not so sure, is that they both exhibit Q2 to Q1 end behavior. Does that make sense, Jeremiah? The blue line is no different from the red line. They have a different graph, sorry, a different graph. They have a different, equation. But in terms of end behavior, they're doing the same thing. They're going from Q2 to Q1. Janaya, go ahead, please. And then Jeremiah, oh, so let me just say one thing. So Jeremiah, you say you're good now. Okay, sorry, Janaya, please go ahead. They have similar end behavior. That's what I'm saying. The end behavior is the same because they're both even and because their lead coefficient is positive. That's what makes them have the same. That's what dictates end behavior. What dictates end behavior is having the same lead coefficient, not the same lead coefficient. Let me say that. Let me say that again. Having a positive lead coefficient and having a odd or even degree. In this case, it's an even degree. That's what makes them have similar characteristics. They're not the same, but they have similar characteristics. So how do we know it's Q2 to Q1 again? Thank you, Kayla. And I'm always going to thank people who ask the questions. What I don't like is when people don't get it and they just sit there and not ask. So Kayla, thank you very much for asking. How do we get Q2 to Q1 again? Because the function, this red line is, remember, this is 2 over here. Oh, sorry. Remember, this is quadrant 2, this is quadrant 1. So this function, this red line here, is starting off in quadrant 2 and eventually ends up in quadrant 1. The same thing, Kayla, is happening with the blue line. The blue line starts off in quadrant 2, and yes, it goes through quadrant 3, it goes through quadrant 4, but ends up, that's what I call end behavior, it ends up in quadrant 1. So reading from left to right, Kayla, yes, we always read from left to right. So that's why I wouldn't say 1 to 2, we'd say 2 to 1. Thanks, and thanks again for the question. Okay, so we've talked about the end behavior now in terms of the x going to minus infinity and y going to positive infinity. So as I go this way, right, if you follow my cursor, as I go this way to the left, the function is shooting upward. So as I go to negative infinity, the function is going towards positive infinity. How about on the other side? As x tends towards positive infinity, where's the function going this time? So as x tends to, it's behind the other blue box. So let's see if anybody can get that first. All right. As x tends, so as I move this way, as I move towards positive infinity, where's the function going this time? What would you say the answer to that is? Anybody? As I move to positive infinity, as x that is moves towards positive infinity, where's the y going? Nobody not sure? Isn't the function moving up again still? Right? Isn't that what the function is doing? Right? So as x moves towards positive infinity, y is also going towards positive infinity. All right, there you go. Okay, still positive. All right, good. We have one more. What happens when you have a quadratic function with a negative a? That's okay. That's okay, Travis. Um, I'm sure that most people figured out what positive means. Anyway, let's get to the last graph. Now, this graph is a quadratic. The red line is a quadratic. As you can see, it opens down. And you know that a quadratic would open down if the a was negative. Right? The negative on a quadratic would give you that kind of graph. Okay. So here's what we need to figure out now. What quadrant am I starting off with and what quadrant am I ending up in? Q what to Q what? Joel thinks Q3 to Q4. Emily and Isaac, look at that. A whole bunch of people think that, okay, good. So Q3 to Q4 is that last end behavior, right? And remember, the quartic function, which is the blue line, behaves exactly the same way. That quartic function moves through every single quadrant. It moves through quadrants 1, 2, 3, and 4, but where's it ending up? That's the question we're asking, right? What's the end behavior of the function? So the end behavior is where the function is ending up. It's ending up in, it starts off, first of all, from one end at 3, and on the other end at 4. So that's what we're doing in this one. That's what we're saying in this one. Now, let's talk about the other way of describing end behavior, right? If I were to ask now what's behind that blue box, the first part of that blue box is what happens as x tends towards minus infinity. Where's the function going? As x tends towards minus, as the x goes to the left, right? As I go this way along the x-axis, right? Where's my y going? Right? Can anybody answer that question? So as x tends towards minus infinity, what's happening to the y's? Where's y moving towards? I get some negative infinities, and that's absolutely correct. So so as x goes negative, y goes negative as well. Thank you very much to all of you who said that. And on the other side, as x tends towards positive infinity, where's the function going on the other side? Right? And I see that most of you have gotten that right as well. As x tends towards positive infinity, y is still going toward the infinity. Okay? So there's your answer. It's Q3 to Q4. And the other way of saying that is to say what we just said. That x tends towards minus infinity, y tends towards minus infinity, x tends towards positive, y. Let me take you back to the first page now, which is going to make much more sense now. Go past the salmon here. Let's come down here. Even powers will only go in one direction, up or down. What does that mean? Let me show you. Even powers, so that's like the odd number ones, sorry, the even number ones, they either go both up or they go both down. That's what I mean by one direction. Is it the both ends are pointing up or both ends are pointing down if it's an even number? Sorry for disconnecting. Yeah, I saw that. Okay, all right. So that's what even powers do, right? Whereas for odd powers, they both go up and down. So what does that mean? Such as the ones here. One side is down, one side is up. One side is up, one side is down, right? So they point in both directions is what we're saying for the odd number one. So the odd degree functions. One points up, one points down.